Boy, are you guys in for a treat today. We get to cover section 3.5, implicit differentiation. It's going to differ from what we've been doing. We've been doing something called explicit differentiation, where on explicit differentiation, I got everything solved for in terms of x. So I have y equals something. As you can see, y is on the side by itself. However, some functions are just easier to describe implicitly. For instance, our friend the circle here. We're going to come back to him in just a minute. As you can see, it's not solved for y. I could solve it for y and end up with a plus or minus and a nasty square root, but sometimes it's just going to be easier to go ahead and just differentiate this function implicitly. I've also included the folium of Descartes down here and its graph. And what we're going to be doing is we're going to be looking at differentiating this function and finding the slope of the tangent line anywhere on this graph that's down the bottom right-hand corner of your screen. So fortunately, we don't need to solve an equation for x, like I've already said. Instead, we're just going to use a method called implicit differentiation. So I'm going to try to have it make sense to you as to why implicit differentiation needs to work, or is going to work, but later on, we're going to get shorter and shorter with our notation as we kind of realize what is going on. So here's that circle I promised you. Okay. It wants me to differentiate. I'm going to work part A first. It wants me to differentiate, and I'm always going to differentiate with respect to x unless they tell me otherwise. So what's going to happen is you're going to be differentiating both sides. Okay, so if I differentiate each individual one, remember if I differentiate this x squared right here, that's easy. That's what we have been doing, 2x. But something weird happens whenever I'm going to differentiate with a plus sign. Differentiate with respect to x, the y squared. Whenever I do that, what I'm going to do is I'm going to change this so that I can differentiate it with respect to y, and then multiply it by dy over dx. Now, I want you to look closely at this. If I actually cancel these dy's I have on top and bottom, I get right back up to where I was. Okay, but I'm gonna pull these down because this is going to be my rule I use anytime I differentiate a term that has a y in it. So now I know that if I differentiate this function with respect to y, this part right here just gives me 2y. And I'm left with this dy over dx. I'm going to use Leibniz notation just for a little bit on that, and we'll switch back and forth some today. And then finally, if I take the derivative, let's see, I got an equal sign in there. If I take the derivative of a constant, I'm still going to have 0. Nothing's new there. So the only part that's really new with this is what you see in red right here. So if I write together everything I have 2x plus 2y, and that dy over dx tags along with it, equals 0. Well, remember what I'm looking for. I'm wanting to find dy over dx. I'm wanting to find I want to differentiate y with respect to x still. So if I just solve this for dy over dx, I'll be in good shape. So I subtract off the 2x. I'm going to divide both sides by 2y. So I get negative 2x over, I do a positive 2y. So the derivative is going to be negative x over y. Now, if we switch over to Newton's notation, I think that you guys will like that a little bit better, but I want you to, it's easier to understand with that Leibniz notation. But now, whenever I'm looking for an equation of the tangent line to this circle, okay, think about what this is. This is actually a circle centered at 0 with radius 5. And so 3, 4 would be about right here. I'm wondering what the slope of that tangent line is right there. Obviously negative. Let's see what happens. Unlike what I've done before whenever I did explicit differentiation, this time I need to use my x and my y. Okay, so to figure out what my slope's going to be, I'm just wanting my derivative with 4 and 3 plugged in for x and y. Negative 3/4. That makes sense. For this to be about negative 3/4, I like that slope. From here, I got a slope, I've got a point. I'm ready to go with point slope form. So I get y equals negative 3/4 x. Let's see, this is 9/4. And if I add 4 to both sides, that should give me my equation. I think that's going to be 25/4. So 16/4, 16 plus 9. Yeah, it's going to be 25/4. And so this is the equation of my tangent line. So really the only thing that we have new in this section so far is just that I'm going to have this, anytime I take the derivative of something with a y in it, I'm going to have to put that dy over dx. Okay. Let's try it again. I got one in a minute I want to see you try, but I'm going to step it up a little bit from this first one. Taking a little longer to erase there. Okay, so I'm going to work this one a little bit different. Okay, so keeping in mind that anytime I take the derivative, I'm taking the derivative with respect to x, but if I need to switch it to y, I just have to throw a y prime after it. So the derivative of x cubed is just going to be 3x squared. Nothing going on with y there. I have to think about this a little bit differently here in a minute. If I take the derivative of y cubed, there's no x in there. So I can take the derivative with respect to y, but I need to throw either a dy or a dx after it, or if I switch back to Newton's notation, it's just simply going to be a y prime. Now, the derivative's right side is going to be tricky. Here's how I see it. I see it as 6x times y. Some people see it as 6, and they pull the 6 out in front, and they just do x times y and use their differentiation rules on it. Either way you think of it, we have a product rule happening on this. So be really careful with this. I'm going to call this the first, and I'm going to call this y my second. So derivative of the first would be, I'm color coordinating this, 6 times the second would be y. Plus the first, well, the first is just 6x, and the derivative of y. Well, the derivative of y is going to be 1, but I took the derivative of y. So for me, it makes a little bit more sense if I just say the derivative of y is y prime. And look at your directions on this. It's just wanting you to find y prime. So what I'm going to do is I'm going to get everything that has a y prime over here on this left side. So that means I'm going to need to subtract off that 6x y prime. And if it doesn't have a y prime, like this 6x term, and like this negative 3x squared term, or I'm going to subtract it over, becomes negative 3x squared, I'm going to move it over to the right side. So that's going to allow me to solve this for y prime, because now everything on the left side has a y prime in common. So I can factor it out, and I just have a single y prime to solve for it. So if I divide both sides by what is in parentheses, I get my derivative equal to this function. That's not a function. My derivative is equal to this expression, I guess. Book might clean it up a little bit. It looks like everything has a 3 in common, so let's go ahead and call that this just divided a 3 off the top and the bottom. And that's probably how the book will have it. That looks a little bit better. Now we got some follow-up questions on this. Hopefully we have room. It says find the tangent line at 3, 3. So find the tangent line at 3, 3. Let's see, I haven't used a lot find a tangent line at 3, 3, what that means is I'm going to be plugging in 3 in for x and 3 in for y to get my slope. Okay? So if I plug in a 3 in for that y, that gives me 6. If I plug a 3 in for that x, that gives me a 9. 3 in for the y, and that's a 9. 3 in for this x on bottom, that's a 6. That's negative 3 over positive 3. Should be a negative 1. I've got a slope, I've got a point, slope, 1. Plus 3, plus 3, would be plus 6. It's kind of hard to check the graph on this to see if that actually does make sense because we don't have an explicit function. You might be able to find a website that will allow you to plug in an implicit function. But I know our graphing calculators, without digging in too deep into them, it's kind of hard to get to the graphing implicit functions. Think it once more. Oh yeah. So at what points on the curve is the tangent line horizontal? So I'm going to need some room on this. Maybe I can work it down the side right here. Okay. So, is this all together? I'll move the derivative up. Ooh, that was too far. Just like vanished, didn't it? So I've got my y prime up here. I'll work with it. Now, if you remember, in order for the tangent line to be horizontal, I'm interested in where it's equal to 0. More importantly, wherever it's equal to 0 on this function that is a fraction is just going to be whatever makes the top equal to 0. So let's take a look at it. We got 2y minus x squared. I'm interested in where it is equal to 0. Well, that's going to be at 2y where it's equal to positive x squared. If I divide both sides by 2, I get x squared over 2, or 1/2 x squared, whatever you want to call it. So that's the relationship between the x and y that I have. But however, if I go back up to the very beginning problem, that I had an x cubed, I think it was plus y cubed equals 6xy. The very first problem I had, I want to know the points. I don't want to know the relationship between x and y. I want to know the points. And so if I use what I know right here, I know that my y is equal to 1/2 x squared. And what I can do is I can plug in this 1/2 x squared in for both of those y's, and now I just have a single function that its only variable is x. And so most algebra students will be able to solve this just to get x by itself. Let's see how we can do as calculus students. If I cube the 1/2, I do believe that makes me 1/8. Something with the power to a power, I multiply their exponents. 1/2 of 6 is 3. Let's add 1 over. X times x squared would be 1 plus 2 would be 3. See the 1/8 here. I'm going to subtract off the x cubed so I can get everything on all my x cubed on one side. Now right here, I see that I can, it's kind of weird on this. Let me see how I want to finish this up. I'm going to finish this up a little bit different than what the book does. I'm going to go ahead and subtract off this 2x cubed back over and factor out the x cubed. I normally work it different, but I'd rather you see that this x cubed right here might equal 0. And so there's one point where it has a horizontal tangent line. If I plug, it's going to be at 0 something. Let's put it in green over here. 0 something. Okay. And then right here, I've got this factor. So 1/8 x cubed minus 2 could equal 0. Well, if I add 2 to both sides and then multiply by 8, that'd be 16. If I take the cube root of 16, I'm not too sure what the cube root of 16 is. I'm not real fond of decimals on this. I know I can take the cube root of 8. Maybe that'll help. Cube root of 8 is 2. So 2 times the cube root of 2. that would just be like 2 to the 4/3. We'll see whichever one we need on that in just a minute. All right, so I'm just going to use 2 to the 4/3 on that. If you want to decimal that out, you'd probably be good because 2 to the 4/3 is not just a real nice number. So it wants to know the points on this. Well, luckily over here I have an equation that is explicitly solved for y. So when x equals 0, y cannot be 0. And I think I'm just going to decimal this out. If I end up putting 2 to the 4/3 in there, it gives me like 3.17 or something. So you can double check me on that, but I plug in that 2 to the 4/3 into this x just like I did 0. Those should be my 2 points where the tangent line on this curve will kind of level out. Oh, sine and cosine want to play, huh? You think you guys can handle this one? Let me see what's next real quick. I know there was one I wanted you guys to work. Yeah, I want you guys to work this one. Okay, so we're gonna pause the video for a second. And you pause the video. You work it out, I'll work it out, and you can come back and see all my steps if we don't get the same answer. I would accept either of these red answers down here at the bottom. One of them has a lot of negative signs in there. It can clean up if you factor in negative out the bottom. And that looks a little more pleasing to the eyes on the right side, so I'm told. Alright, second derivative. Second derivative. This one's going to work a lot like one we've seen already. Okay? We're going to have to work these in order, where we find the first derivative and then the second derivative, but we'll need to do, of course, the first derivative first. So I'm just going to start off with, so we're used to just writing y prime equals. I'm going to start off with just my 4x cubed plus 4y cubed y prime. Pick derivative of y, throw that after. Okay. And so, like I said, very similar to the circle we did earlier. Divide both sides by 4y cubed. I think we just get negative x cubed over y cubed. You can double check me on that. But now I'm wanting a second derivative. And you're thinking this might not be too bad, because if I take the derivative of y prime, it gives me y double prime. And then here I just have a quotient on the right side. So I just need to do a quotient rule to this right side. Yeah, you're right. And so first off, we need to really choose, I don't know if this is combined. Yeah, we really need to choose the negative to go at the top or the bottom. Either that, or you can just throw a negative out in front of your whole big fraction. I'm not going to do that. I'm going to say the negative goes with the x cubed. And so we jump way ahead. So that's going to give me negative 3x squared for the derivative of the top, times the bottom minus the top. Well, that would just be plus x cubed, if you don't mind me going and combining those, times the derivative of the bottom. Derivative of the bottom. Ooh, we got that y prime back in there. It'll be okay. All over the bottom squared. Y cubed squared, something with the power 2 power, multiply the exponents. 2 times 3 is 6. You're thinking, wow, that's not bad. I think we're done. No, I really would rather not have that y prime in there. So we could clean this up a little bit. There's a couple things we can do to it. This first step, I'm going to go ahead and pull that 3 out in front so I remember it's there. So my y prime, remember, is equal to negative x cubed over y cubed. So that plus sign I changed in the middle is going to have to go back to a negative. And that's an x. And I'm wanting a y. There we go. They might be thinking, well, that looks pretty good. really rather not have a fraction inside of a fraction. So, let's see. What do I do to it? Let's just multiply everything by y cubed. That's the fraction, the denominator of the fraction that's in the way. So that's going to be negative 3x squared. That's going to be y to the 6th plus 3x squared. So check this out. This is cool. That's going to cancel. And so I'm just going to be left with y squared negative x cubed all over. Now I'm down to up to y to the 9th on the bottom. Well, I've got some terms in common, or some y's in common in every single term. So I can definitely pull a y squared out of everything. So let's do that first. Let's pull out a y squared. So that'll be a y to the 4th. I'm going to go ahead and pull that through. Negative 3x to the 5th. So I divided that by y squared. Let's divide the bottom by y squared as well. Now take it down to y to the 7th. Hopefully I'm on the right spot with this. I feel like I'm missing an x somewhere. Where did I lose an x at? You see it? X to the 6th. This 3 right here. Just randomly changed to a 2. Were you guys not going to tell me about it? Man, I thought we were friends. So, easy fix right there. That will be a 6. I feel better about that. I think I could get even more simplified than that. Because see, I have a negative 3x squared in common on top. So let's just see what happens if I pull that out. I'm left with y to the 4th plus x to the 4th over y to the 7th. That does look better. I think we could go a little bit further. I'm running out of room. I think I can go ahead and change this x to the 4th, y to the 4th to 16. I know you're thinking, oh man, the bulb guy's lost it now. I assure you I have it. I assure you x to the 4th plus y to the 4th is equal to 16. You like that trick? So I can finally get my final answer. Negative 48x squared over y to the 7th. That would be my second derivative. That was fun. I have fun with that one every year whenever I get to work it. Now, there's a couple homework problems that call for something called an orthogonal trajectory. An orthogonal trajectory is simply, it says that every curve in one family is orthogonal to every curve in the other family. I've hardly ever, I don't know if I've ever in 15 years had a student tell me what an orthogonal trajectory actually means. So let's just take a look at it. I want to show that every curve in this family, x times y equals c, is orthogonal, whatever in the world that means, to every curve in this family. Looks like they're x squared minus y squared. I think it's a hyperbola. Well, x times y, that's also hyperbola, but it's been rotated. So, obviously we're going to need a derivative here. So I'm going to start with the x, y times c. That's a product rule. So derivative first, that's just 1, times second, plus the first, times the derivative of the second, derivative of y, is going to be y prime. Let's just solve this for y prime. So if I subtract the y and divide by x, I get negative y over x for that derivative. Interesting. Now let's do x squared minus y squared equals k. 2x minus 2y y prime. And then k is a constant, so I'm going to take that to 0, just like I did to c earlier. So I get negative 2y y prime equals negative 2x. Looks like we've done a similar math to this. Oh, wait a minute, I get two negatives. That'll be a positive xy. Can you tell me how these two relate to each other? They are negative reciprocals. If we're negative reciprocals, my Algebra 1 teacher taught me that if I have two slopes, like I have here, that are negative reciprocals of each other, that means they're perpendicular lines. And that is what orthogonal means. It means that they intersect at right angles, and that they're perpendicular, or we can also say that they are orthogonal. Well, we didn't have any differentiation rules for our inverse trig functions. They're feeling kind of left out. So let's come up with a differentiation rule for sine inverse of x. This little spot bothering you? I got you. Okay. So we're just going to come up with one. Instead of just telling you what it is, I'm going to come up with one to show you where it comes from. Okay. So my definition of sine inverse of x equals y says that this is going to be true if and only if x is equal to sine of y. And then we're able to stay in the domain. We'll just assume that everything's good on the domain. So everything looks differentiable here. Okay, so not sure how to differentiate this one. But I know how to differentiate x equals sine of y, because with respect to x, if I differentiate the x, that gives me 1. If I differentiate the sine of y, that's going to be cosine of y. But I've also got to multiply that by y prime. Okay, so I'm going to end up with 1 over cosine y is equal to y prime. Well, that's good and all, but man, they started me off so good right here with a nice explicit function. So I'm wanting to give them an explicit function back for the derivative of sine inverse of x. So what to do with this? Well, I'd really like to get rid of the cosine y. Well, I know that feels like I'm going to make a grab here at this, but I think you'll kind of see where I go with it. I know that sine squared plus cosine squared equals 1. And since we're talking about y, I'm just going to put it back. I'm just going to put all these in terms of y. And so that means that cosine squared y would be 1 minus sine squared of y. So cosine of y would just be the square root of 1 minus sine squared of y. Well, how does that help me? Well, it helps me because the very first thing that we stated was that in order for y equals sine inverse of x, that can only be true if and only if x equals sine of y. So just a slight little substitution right here. I get 1 minus x squared. Meaning that my derivative, remember this is what cosine is equal to, is going to be 1 over the square root of 1 minus x squared. That is going to be the derivative of sine inverse of x. I know that seems really weird, doesn't it? Right? But your Pythagorean identities, I hit hard on them last year. They will come back into play. If we're needing to derive the derivative of an inverse trig function. Okay? So you try it for tangent. Use kind of the same template I just did. I'm going to work it out. Talk to myself while I do it, while the video is paused. You hit pause. You try to figure it out. We'll be better off for it. Then we'll see if we got the right thing. You got a little bit easier one than I did. Okay? Just so you can kind of follow my arrows, I went down and then I brought it up. Okay, so I didn't have to take the square root on this one because it just fits straight into my Pythagorean theorem of secant squared equals 1 plus tangent squared. You know what? This is supposed to be a y. We're just going to act like that was a y already. All right, we're good. So here's all of my inverse trig functions. Write them down, memorize them, put them on top of your homework sheet so that you have them. These are all going to be fair game for the upcoming assessment. Okay, so there's a couple domain restrictions on there. Those are kind of no duh on it. We're going to try to avoid those. But any of these that I ask, you should be able to take the derivative of. And so now what that's going to allow us to do is to mix this with our chain rule and a product rule. Okay? So let's try this chain rule first on the left. Now this is all going to be explicit. So the whole point of having a y prime in the middle of something, it's gone for now. It's just in this section because in order for these to work, implicit differentiation needs to take place. Okay? So I'm looking to differentiate this. Before I get going on this, I see a need to rewrite this. I'm going to try to avoid that quotient rule. I hate using a quotient rule where I'm taking the derivative of 1. Okay? If you do, you're going to get the same answer I'm about to get, but I'm just going to change this to sine inverse of x raised to the negative first power. That way I can just do a chain rule where the negative 1 comes down in front, and I lower the exponent by 1. So that's the derivative of the outside. I got to multiply that by the derivative of the inside. We said a while ago the derivative of the inside, derivative of sine inverse of x, is 1 over the square root of 1 minus x squared. Kind of put everything together here. Got a negative out in front. We put it on top. I've got a sine inverse of x raised to the negative second power. I'm just going to put that on the bottom, so I don't have to worry about. I can't do that, but I can leave it sine inverse of x and raise it to the positive second power and just have it in the denominator. And then this was already in the denominator. He's going to hang out here. That doesn't simplify any. We're good right there, and I like that answer. Let's see how this is going to work for x times arctangent of the square root of x. Now, I just see this as one product rule right here. I only have two x's in this, so there's only two functions of x. One is x, one is arctan of the square root of x. If you want to change up the tangent inverse, please do. Okay. Now I'm looking for the derivative. So, I'm going to use my product rule. I take the derivative first, times the second, plus the first times the derivative of the second. Okay? Derivative of the second, arctangent of x, said it was going to be 1 over 1 plus x squared. Well, here's the problem. I'm not taking arctan of x, I'm taking arctan of the square root of x. So it's 1 over 1 plus the square root of x squared. Then I have a chain rule tacked on to the back end of it. 1/2 x to the negative 1. So I've got a little bit lengthy back there in the back. Okay, so still got to look at that chain rule. If I'm taking arctan, arcsine, arccosine of anything other than x, just like for sine, cosine, and tangent, I've got to do a chain rule on it. Not much is going to happen to this first term. I've got arctan of the square root of x. Right. And then if I take this x and then x to the negative 1/2 and subtract their exponents, that gives me x to 1/2. Or square root of x, if that's more to your liking. Got a 2 on bottom. And yes, if I square a square root, it just gives me an x. I would accept this if you wanted to. You could put a square root over this and not have the 1/2. That would be fine as well. There's the homework problems for this year. Make sure it matches what I put in Google Classroom or whatever learning medium I'm using online. So work through these. You should have some questions on them. I'm looking forward to the homework day.